To enable GSM customers to use speech, fax and data services wherever they are within the network, information and data must be exchanged within as well as between different networks. This process is called signaling. To set up a call, signaling takes place between subscriber interface points, that is, between the user and the network, as well as between different network elements. To make sure that the individual elements through which the information travels can understand each other, they must, as it were, agree on a common official language. This language is specified by protocols. The protocol used in the network subsystem, NSS, is called Signaling System Number 7, or SS7. SS7 is based on the Open System Interconnection Model, also called the OSI Reference Model. We'll now illustrate in general terms the OSI Reference Model with an example from business life. A car manufacturer B orders 1,000 tyres from supplier A. This deal is concluded and signed by two managers at the highest level. For the two managers, only the outcome of this business deal is important. The process that takes place in the lower hierarchy to get the tyres from the supplier to the car manufacturer does not interest them. The managers rely on their purchasing and sales departments, which will deal with practical details. The car manufacturer's purchasing department, however, only communicates with the supplier's sales department. As soon as the financial transactions are concluded, the goods can be delivered from A to B. The purchasing and sales departments are not interested in the practical details of delivery. At the supplier, the warehouse workers must pack the tyres and load them on trucks to get them ready for transport. As soon as the tyres arrive at the manufacturer, the warehouse workers will unpack the tyres and store them. In summary, we can say it's always several levels of a company that collaborate in a business transaction. The higher levels give the lower levels instructions without paying attention to the details of the processes. Communication between the two companies takes place only between peer levels. With the OSI model, it's similar. OSI is a reference model consisting of 7 layers that are based on each other. Each layer has its own tasks. The lower layer always provides support functions for the layer above. For a layer, the data transported in the layers underneath is irrelevant. Communication only takes place between the elements of the same layer. This type of communication between elements belonging to the same layer in different systems is known as peer-to-peer communication. The layers take over the following tasks. The lowest layer, layer number 1, is the physical layer. It's responsible for transmission, encoding, and modulation. Layer 2 is the data link layer. It's responsible for the signaling link management and data security. Layer 3 is the network layer. It contains the information needed for switching and routing and handles call setup, supervision, and clear down. Layer 4 is the transport layer. Here, the peer-to-peer connection's data flow is controlled. Layer 5 is the session layer. It handles the connections for application processes as well as charging. Layer 6 is the presentation layer. It takes over the transfer of application-oriented formats as well as encryption and translation. At the top resides layer number 7, the application layer. It's responsible for the application protocols and the user interfaces. The basic SS7 version consists of 2 parts. The message transfer part, MTP, which is responsible for message transfer, and the telephone user part, TUP, on the user's side, which receives, sends, and acts on these messages. Let's turn our attention to MTP first. The message transfer part, MTP, represents the basis for the entire SS7 system. It transmits messages between network elements. MTP is composed of 3 layers. MTP Layer 1 defines the physical and electrical characteristics of the connection. MTP Layer 2 supports the error-free transmission of signaling messages between neighbouring network elements. MTP Layer 3 is responsible for taking the message from any element in a signaling network to any other element within the same network. While MTP is responsible for message transfer, the telephone user part, TUP, represents the protocol used for sending, receiving, and acting on these messages from the user's point of view. TUP handles call setup, call supervision, and cleardown, and exists for normal public fixed networks, which are also known as public switched telephone networks, or PSTN. With the introduction of the more capable ISDN network, some extra sets of messages became necessary. These features are contained in the ISUP, which replaces the TUP. To guarantee virtual connections and connectionless signaling, that is, signaling which is not bound to a call, another protocol layer on top of MTP is required, parallel to TUP. This is the signaling connection and control part, SCCP. TUP and SCCP take over different tasks, but both make use of the services provided by MTP. In contrast to MTP, SCCP uses sequence numbers to make sure that messages arrive at the receiver in a determined order, so a virtual connection can be guaranteed. SCCP also enables the routing of signaling messages across multiple networks in the absence of a call. This layer structure, consisting of MTP and TUP ISUP, as well as SSCP, represents the SS7 protocol, which is the protocol used for signaling within public switched telephone networks and ISDN networks. In GSM networks, signaling is not as easy as in a fixed network. This is because, due to the network architecture, a digital mobile radio network makes much higher demands on signaling. GSM requires a considerably higher amount of non-correlated signaling information. After all, it must be considered that the GSM customer is mobile, in contrast to the user of a fixed network who telephones from a fixed device. Therefore, the mobile station must continuously be provided with localization signals to enable the location update. The location update is an example of a non-correlated communication between the phone and the network. To guarantee that the signaling demands in GSM networks are met, additional standard sets of messages are required. The following protocol layers are necessary: the base station subsystem application part, BSSAP, the transaction capabilities application part, TCAP, and the mobile application part, MAP. The base station subsystem application part, BSSAP, is a protocol layer responsible for communication between the MSC and the BSC in GSM. BSSAP is responsible for the entire management and control of the radio resources in the BSS. It resides on top of the signaling connection and control part, SCCP. The Transaction Capabilities Application part, TCAP, is a protocol layer which resides directly on top of SCCP. TCAP is able, for example, to organize a complex dialogue between an MSC and an HLR, including a sequence of successive requests and replies. TCAP functions like a secretary's office, where many different requests are brought into the correct sequence and distributed. TCAP handles the access to databases like the HLR or the VLR. It must exist so that a higher protocol, the mobile application part, MAP, can be used. The mobile application part, MAP, is a GSM-specific protocol for non-call-related applications between elements in the NSS. MAP resides directly on top of TCAP, which can be used as a secretary's office by the MAP, and which coordinates and guarantees a smooth MAP communication. A A map-based communication takes place when data is exchanged between NSS elements in the absence of a call. This is the case, for example, with normal call setup. To put a call through to the subscriber, the gateway MSC must request necessary routing data from the HLR. Thus, there's no data exchange between the GMSC and the HLR without the actual call being routed to the HLR. In such cases, the network relies on MAP, which is used for signaling communication between NSS elements. Please note, in the MSC-MSC communication, MAP is only used for non-call related signaling. To forward a call from an MSC to another MSC, TUP or ISUP is used. Not every GSM element must be able to understand every language. Consequently, only those protocol layers which the network element actually requires for carrying out its task need to be implemented. A BSC, for example, will never need the TUP protocol because call supervision, which this layer supports, is not its task. In the following lessons, the SS7 requirements of the individual GSM elements will be introduced. As in all the other elements, MTP is the basis protocol in the MSC VLR. Without it, there would be no SS7-based signaling. Furthermore, the MSC needs TUP or ISUP for call supervision. Since the MSC communicates with the BSC and the HLR, it also requires BSSAP and MAP, which are both based on SCCP. The use of MAP requires the presence of TCAP. Thus, the MSC, as the key element of the network subsystem NSS, must include the whole range of SS7 protocols. The HLR is not responsible for call control, and therefore does not need TUP ISUP. Furthermore, since it doesn't have to communicate directly with the base station controller, BSSAP is not implemented in the HLR. Thus, only the four protocols MTP, SCCP, TCAP and MAP must be present in the HLR. Normally, the BSC would manage on BSSAP, but since in modern networks BSSAP is based on the SCCP protocol, whose functionality in turn requires the presence of MTP, the BSC contains MTP, SCCP and BSSAP. Communication between network elements always takes place using the relevant protocols, each protocol relying on the protocols of the layers below. For example, the signaling from the MSC to a PSTN for call setup is carried out by TUP, which is based on MTP in both elements. Or, if an MSC wants to know the current location of a subscriber, it communicates with the responsible HLR using MAP. In this communication, TCAP, SCCP and MTP are required. The BSSAP protocol, on the other hand, is only needed by the MSC when it wants to communicate with the BSC. Whereas the elements in the network subsystem use SS7, further protocol types are needed in the base station subsystem. The BSC and BTS communicate using the Link Access Protocol for the ISDN D channel, or LAP-D. This protocol is also used between the end user and the net in ISDN networks. A slightly modified version of the same protocol also exists between the BTS and the mobile station. Due to the modifications imposed by the characteristics of the air interface, the protocol is called LAP-DM. The message structure within LAP-D resembles that of SS7, but it's limited to the support of point-to-point connections. Between the NSS elements, data is either exchanged over copper cable or optical fibre or via microwave. All NSS interfaces offer data rates of at least 64 kilobits per second. 2 megabit per second connections are the rule. The protocols are based on the SS7 standard. Two kinds of information are transferred over the different interfaces. Signaling information, such as addressing and mobility data, and user data, that means speech, fax, and data messages. Between the NSS elements, we find the following interfaces: Note that the Mobile Services Centre, MSC, and the Visitor Location Register, VLR, form a spatial unit. Between the MSC and the VLR, we find the B interface. This interface is used to transmit signalling data. The C interface is located between the MSC and the Home Location Register, HLR. It's also used exclusively for signalling data. The D interface provides the connection between the VLR and the HLR. Like the interfaces B and C, it transmits signalling data. The E interface is located between two MSCs. Apart from signalling data, user data and speech can be transmitted as well. The F interface is located between the MSC and the Equipment Identity Register, EIR. If an EIR exists, the interface is used exclusively for signalling data concerning the EMI control. The MSCs which provide connections to another mobile radio network, that is, a public LAN mobile network, PLMN, or a public switch telephone network, PSTN, and which are connected to the HLR, are also known as Gateway MSCs or GMSCs. The interface between the visited network and a GMSC transmits user and signalling data. As a rule, every MSC can function as a GMSC nowadays. From the network operator's point of view, this is cost efficient, because the more MSCs can function as gateways to other networks, the longer a call can be routed within the own network before it's handed over to a different network.